Okay. Okay. Hello to everybody, and welcome to the third lecture that, due to my clumsiness, I'm not going to start because I'm trying to let the presentation start, but I'm not able to do this. Okay. Perfect. So thank you again for being here at this in this early time in the morning. I'll as usual I begin by clearing what's going on. We've been facing and we've been exposing how to deal with variables that do influence each other in the case when we are able to track, to measure all the variables that we need in order to understand the problem. But reality, of course, plots against us. So it is often the case that we perfectly know that there are missing variables, that there are variables we are not able to measure. Once during a press release, former US politician Donald Rumsfeld said that there are three kinds of menaces. There are known menaces that we know and can measure. There are known unknowns, that is, variables that we know that exist, but we can't measure. And there are unknown unknowns, that is, menaces, dangers that not only we can't measure, but we are actually unaware that they exist. For these sentences, Rumsfeld has been blamed and mocked for several years, but actually Donald Rumsfeld, despite being politically not sometimes so clever, in this case Rumsfeld was perfectly right. Unknown unknowns, so dangers of which not only we can't measure, but we are unaware of, can be very dangerous. In this lecture, we're going to see how to treat with known unknowns, that is, things, variables, effects that we are aware of, but that we can't measure. And we will learn how to deal with this kind of problems. We saw on the last lecture that we can always decompose in a recursive way a Bayesian networks, and that we can express the probability of a node, a variable associated to a node, to get a given value, conditioned on the fact that we know the values of the parents of that variable, that is, the variable that have an arrow pointing from them to the x, to the variable that we are interested in. And this helped us in saying that we can always calculate the effect of an intervention, the effect of the do operator, by just taking the product of the conditional probability of the nodes that are not in B, that are not in our intervention set. That is an operation perfectly equivalent to the operation of erasing all the arrows pointing into our intervention set, deleting all the arrows that are pointing into the variables on which we act, on which we write do. So whenever we write do, open parentheses, some set of variables, this means that I have to erase all the arrows pointing into that variables. I know perfectly that you understood this, but I begin to have a certain age, so I have to repeat things to myself in order to be able to recall them. You know, when one arrives at my age, there are two main problems. The first is a leakage, a leak of short-term memory, and the second is a leak in short-term memory. So this product formula we can apply always when we have all the variables that we need, but sometimes it happens a very bad thing, that we have not all the variables that we need, and we know for sure. Sometimes we suspect, sometimes we know for sure, but it happens, and it happens often, that we are aware that there is a common cause, that there is something hidden that we can't measure. Take, for example, we will see more concrete example, but to honor Luca Pappalardo and his team that raised finally Serie A after 23 years, if I do not fail, after the first time, we will speak about football. Imagine that you know that the behavior of a player A, and a player B of the same team is influenced by the tactics, the instructions that were given to them by the coach. And it's really, really difficult to measure a tactic unless you are not given precise data, or unless you are can't speak to the coach. And if you can speak to the coach, often your ideas will be messed up more, because these people sometimes can't or won't or will not express themselves clearly. So you suspect that there is a spurious correlation, you know that there is a spurious correlation, but you can't measure for it. A classical example has been the suspect, and here I'm going to go a little bit on in advance, just to see. This was a classic example. During 50s and 60s, people begin to debate why, if smoking was causing cancer or not. And some people inferred that there was a smoking gene that influenced both the carving for smoking, both the carving for nicotine and the cancer. And in the 50s and 60s, if you ask a statistician to deal with the problem of the augmented amount of lung cancer, they would point to asphalt of the street and to motors, to gasoline and to gasoline motors, not to smoking. So this is a classic example in which you can't measure a smoking gene. Maybe today you could, according to the fact that you should be able to identify a smoking gene and understand how to find it. But in the 50s and the 60s, it was absolutely impossible. So let's go and let's go to this 2-hour problem. Sometimes this happens. How can I estimate the probability of something that I can't measure? Well, is extremely simple. I don't do it. I won't try to fool myself, trying to invent or trying to define impossible measures of something that I sometimes can't even define. let it alone to measure it. I don't do it. What I try to do is I try to express that this probability, these conditional probabilities and this do in terms of what I can measure. I try to work on my graph, on my pathway, in order to understand if hidden in this spurious correlation, hidden in these pathways, there is a way to reconstruct this probability without the need to pass from that point. So the basic idea is to express the truncated product formula, the formula that we saw before here, just not in terms of all the parents of the variables, but in terms of some of the parents of the variables. And we will begin with a simple example and then go ahead. As usual, please, if there is something that doesn't convince you, if there is something that sounds strange, incorrect, or simply not clear to you, please raise your hand and write me on the chat and let me know. I know for sure that in the last lecture I said something horribly wrong. We will fix it, but we will arrive playing with it. So please let me avoid to say wrong things or incorrect things and correct me when I do this. I'm quite sure that you can do it. So the basis idea is to express this truncated formula not in terms of all the variables, but in terms of only some variables. I can be able sometimes to pick the right set of variables that allow me to block all the spurious pathways while leaving the direct pathways active, alive and kicking, and how to combine these in order to get the correct result. And we begin with the first example, that is the so-called backdoor criterion. Here, for backdoor, we mean a spurious correlation that realizes through a flow of information that goes from the x, from the variable that I want to control, on which I want to do something, and information can flow through a pathway that has an arrow pointing into x, pointing into my variable. So, given an ordered pair of variables in a directed acyclic graph, a set of variables z, so a set is a single variable, an empty variable, or a group of variables, satisfies the backdoor criterion relative to x and epsilon, where x is the supposed cause and epsilon is the supposed effect, if and only if z blocks every path between x and epsilon having an arrow pointing into x. And this is the first criterion. And two, no node in Z is a descendant of X. So, as usual in mathematics, the definition is wonderful once we already understood what we are doing. So let's try to do an example and let's see what I do mean. First of all, there is, after the definition, of course, a formula. If I am able to find this set Z, and if this set Z satisfies the backdoor criterion, then I have the formula with which I can transform my expression containing a do in an expression that do not contain any do. if you remember, this is our aim, to be able to express the effect of the intervention just in terms of conditional probabilities, without any do that I can't, of course, define or calculate in mathematical terms in other ways. I have to express this operation in terms of observation probabilities, in terms of conditional probabilities. So this is the backdoor criterion. One simple thing that we can immediately see is that the set of parents of X, if I take all the parents of X, the parents of X always satisfy the backdoor criterion, because the parents of X block every path between X and Y having an arrow pointing into X, because they are the sources of the arrows, of all the arrows pointing into X, and no node in Z is a descendant of X. Since they are all parents, they can't be descendant. So in this case, for the parents, if we have all the parents of X, our problem, our formula coincides with the calculation we did before with the truncated product formula. But what is the logic between the backdoor criterion? Imagine that we have an unmeasured spurious correlation that is between that, for example, rules Z3 and X. The logic is that we block all the spurious path between X and Y. So we block all the flow of information flowing from X to Y through U and Z3, but we leave the directed paths, the one that goes from X to Y in a directed fashion, so by means of the mechanism that we are aware of, and for which we can even write functions, without creating, and this third point is very important, without creating no new spurious paths. We will arrive soon to the third point. The first 2 points are quite logic. We will arrive soon to the third point, that is where I said my mistake last time. And this is where I here suggest you this, and I ask you directly this question. I want to find a backdoor set able to block all the spurious information between X and Y. I have two possibilities in this graph. The one is to block for Z3 alone, and the other one is to block Z3 and Z2. Now, what I'm asking you is just to bet on these two possibilities. If bet, I use bet in a wide sense. I don't want you to answer, because answering may get you a little bit scary of saying I'm saying something wrong. No, I want you to bet. Which conditioning set would you choose to be the correct one for backdoor criterion? The first, only Z3, or the second, Z3 and Z2? Okay, I have already an answer. Wonderful. Someone is not sleeping, and this is wonderful. As far as I'm able to put my... Okay. Please, Z3, Z2, says Andrea Pugnana. I will allow you to speak if you allow me to do so, and so you can explain us why why you are convinced that of your answer. I'm sorry, but I'm not able this time to allow you to speak. So I ask the administrator to let you speak, because okay, please, Andrea.
I should be able to speak.
Yes, you are.
I think that the problem here is that if we condition on Z3, that is a collider, and so we will open a path between Z2 and unobserved.
This is the correct answer. If you open Z3, you open a collider. So it is necessary to condition on Z3 because Z3 is on each and every backdoor path between X and Y. But if you condition on Z3 only, you open spurious correlation between U and Z2. So you have to control for Z2 too. If you remember, last time I said something wrong about the performance of evaluating the performance of a goalkeeper, and I was fooled by the fact that numerically the Z2 was not so important. So it was not leading to huge difference, but theoretically, the theoretical aspect was very different. So in this case, you want to you do have this this problem. You have to condition on a collider. And since you condition on a collider, you can you have to block the other paths. So as a prize, I will shut you off, but I thank you for the observation. So this is one of the wonderful things of teaching, that when you teach something, you understand it quite more. And so we are actually learning things together. So as I was saying, Z3 is a collider, and this opens a spurious path. So we have to condition for the both. How can we demonstrate the backdoor formula? Well, all the demonstration about do calculus rely on the fact that we write equivalencies between the original graph and a modified graph. So we take the original graph, we apply our do operator, and then we calculate probabilities on this new modified graph, and we try to understand the effect of the effect on our probabilities on the modified graph. So in this case, we demonstrate. Demonstrate, as you will see, is not the correct word. Here we show how this rises. For the formal demonstration, we will see not in detail, and we will see in what's coming up, that a formal demonstration is quite long and quite painful, and I will give you all the hints to arrive to that. But the formal demonstration would require all the time of the lesson, about all the 12 hours, and I'm not quite sure that it would be the correct choice. So imagine that we want to do x, that is to force the variable capital X to get the value that we want. This is equivalent to force X to get this value, and we obtain the graph that is on your left without any arrow pointing into X. We have just our feeder, our F, that feeds the correct value, the required, value of the variable into our source. So in this sense, the probability of epsilon condition on do X is equal to the probability on primed on the new graph. That means a condition on Fx. Now, what happens? We can always express the probability of X conditioned on F of Fx by usual laws of probability as a sum conditioned on all the possible value of Z. So it is equal to the probability of X conditioned on Fx is equal to the probability in my new graph, in my modified graph, the probability of epsilon condition on Z and Fx times the probability of Z condition on Fx. In this formula, we can always say that is equal to the probability, and here we are on the second row, on the probability of epsilon condition on Z, X and Fx, because by implication, if there is Fx, then capital X, the variable X, assumes the value X. So I'm not, I'm saying only if it rains, and I say if it rains and if there is water falling from the clouds, I'm saying exactly the same thing, just in two different ways. But since Fx is independent on the non-descendant of X, if you remember, it is the condition 2 of the backdoor criterion, I can always say that the probability prime, the probability modified of Z condition Fx is equal to the probability of Z. In fact, the probability of Z is not conditioned, is not affected by the value of X. It is absolutely indifferent to me if the value of X is comes from natural or from artificial feeding. X do not influence Z. But condition 1, if intervention, if I satisfy condition 1, and if you remember, condition 1 is that Z blocks every path between X and epsilon that contains an arrow into X, then the intervention is indistinguishable from observation. So I can say that the fact of having X and forcing the value of X into X are absolutely indistinguishable as far as I am considering the value of epsilon conditioned on Z and X. So I arrive at the backdoor formula. If you are not sure to having understood well, let me be honest and humble in order to say you that I began to study causality in 2014, and I have another work, but it required me about 3 years in order to begin to understand these things. And what I'm trying to do in these lectures is trying to make you avoid all the mistakes that I did during this process. Reasoning with probabilities and with graph together is not easy. So I'm perfectly aware of the fact that someone saying you this is not equivalent to understand this, not even to be convinced. So if there is any doubt on this process, on this a little demonstration, particular demonstration on this graph, please write on the chat and let me know. But probably things are not, you can follow me, but assuming that some of the things that I say are true. If there is any problem, please raise your hand and let me know. The spirit of the backdoor formula is, as we were saying, that we can do causal calculation even on a restricted set of parents. So parents whose probability distribution calculation is difficult or painful or costly can be avoided. And this is very important because we can sometimes draw a graph in which all the probability are measurable, but some of the probability are some of the conditional probability that we obtain are sparse. There we have a sort of a 5 times 5 matrix, 5 times 5 row, 5 times 5 times 5 times 5 hypermatrix on which many entries are 0. Is a sparse hypermatrix, and I usually want to avoid this situation when dealing with a statistical calculation. I want to grab things together the most that I can. So if I can rely on conditional distribution that are more reliable than others, then I should try my best in order to use that probability distribution and only that. So in this case, even when I have the all the variables that I need, even when I can measure all the variables, remember that some of the variables can add mess to my to my calculation instead of helping me following what's going on. And so backdoor criterion can help me a lot in this kind of operation. So we saw that backdoor criterion is useful when we have an unmeasured path or when we have an unmeasured variable, or when we have all the variables, but I am not quite sure of which, I'm not quite sure of the quality of the data of some of my variables. And the backdoor criterion is will be one of my two workhorse in causal analysis on graphs. But there is still a possibility. There is still a very sad possibility that there is no vector. Imagine this. Imagine the situation that we saw earlier. There is an unmeasured connection, a spurious correlation between my x, the variable that I can control, about which I want to understand the causal power, and y, the effect variable, the things that actually interest me. And if I suspect that there is an unmeasurable vector, there is no vector. I can't condition on something that I can't measure. So I have to find another way. I have to deal with this in another way. And how? How can I do it? And the reason is that I have to exploit correctly what's in between, the mechanism, the Z. I can actually try to exploit the presence of a mechanism between x and y, between the variable and the cause variable and the effect variable. And if I have this mechanism, I can go all my way through and be able to do my calculation, my causal calculation. And we will see in the following a brief demonstration on a simple example again, and then in the next hour, we will see a complete method to be able to infer causal pathways utilizing this criterion by means of a complete set of rules. That is a set of rules that allow me always to find the correct way, and we will deal with this. So let's try to work over this this kind of calculation. Let's note a first thing. The effect, let's try to calculate the effect of x on z, on our mechanism. So there is only a direct mechanism between x and z. There is no backdoor path from x to z because u points toward x and y. So no backdoor path from x to z, if this is the diagram that we want to use. So if there is no backdoor path, if there is no spurious correlation, there are no parents of x influencing z. And this means if we go back to the truncated product formula, that the probability of z, if I do x, is equal to the probability of z conditioned on x. Remember that each time that you have an unmeasured variable, you can, of course, apply the truncated product formula. The only thing that you can't do is to, of course, having that final the value of u into the variable u into your formula, but you can use it to manipulate your graphs and to manipulate the probabilities coming out from your graphs. That's perfectly allowed. You can in mathematics you can use things that you can't measure as far as you want to do numerical calculation on them. So as a first result, what I do is stating that the probability of z conditioned on do x is equal to the probability of z conditioned on x. The second thing that I ask is to try to identify the effect of z on y, the causal effect of z on y. And here I have a backdoor path. Is the backdoor path that goes from z to x, from x to u, and from u to y. And in this case, how can I block this backdoor path? Since you are so clever students, I won't ask you directly because I know for sure that you know the answer. I can't, of course, block on u because I can't measure u, but I can block on x. So I can apply the backdoor formula conditioning on x because I'm sure that x blocks all the spurious correlation from z to y, passing through x and u. So I am able to express the causal effect of x on z and of z on epsilon. Of course, here there is another mistake. The probability, I'm here assuming the probability that Z, capital Z, takes the value, a value Z, a value allowed. Okay, if my my variable is not the variable X, if I weren't registered, I would say that that I did it on purpose in order for you to see if you were aware. But since I'm registered and everything I say can be used against me, I admit it was my mistake. So, given these two, I can philosophically, let's say that if nature forces Z to take the value Z, the probability to see epsilon equal epsilon is, of course, the probability that of epsilon conditioned to do Z equal to capital Z equal to small z. Of course, the probability that Z equals Z by natural law, if we force X, is probability of Z condition on do X equal to X. Let's to understand what I mean. Let's imagine the scheme that I was saying before. The probability that I get cancer if I insert by chemical methods, if I insert tar surgically in my lungs, will be the probability that I have cancer if I make my my lungs full of tar. The probability that I have tar by natural laws if I smoke is the probability, of course, of having tar conditioned on the probability that I smoke. In one case, I'm inserting tar by artificial mechanism. In the one, I'm asking simply, what's the probability of having tar in my lungs if I smoke 20, 40 cigarettes per day? So I'm watching two different mechanisms, and I'm trying to express this in terms of conditional probabilities. Now I try to chain these two. I ask myself, I can express the probability that I have tar in my lungs by natural laws if I smoke. I can express the probability that if I have tar in my lungs, by any means, inserting it chemically, inserting it magically, or by smoking, I develop cancer. I can chain these two mechanisms together and saying that the probability of verifying epsilon if I do X, that is, that I have cancer if I smoke, is equal to the probability of having cancer if I do insert tar into my lungs by every possible mean, times the probability of having cancer, of having tar in my lungs by natural means, probability of Z, conditioned on the operation on X, conditioned on the fact that I smoke. And so by substituting these two, probability of epsilon doing Z and probability of Z doing X, by the formulas, if you remember, that I was able to work out before, I can arrive to this law. The probability of epsilon if I do X is a summation given by the summation on Z and on X prime. It's a dummy index. In this case, you have to be very careful. The probability of epsilon time conditioned on Z and X prime times the probability of x prime times the probability of z times x. So by expressing the intermediate intervention, the probability of y doing z and the probability of z doing x, I was able to reconstruct and to exploit only the conditional probabilities that I know in order to work out the causal effect of x on y without u. If you note, it's easy to note that u is absolutely absent from this expression. And I'm aware that that the effect of that workout of this mechanism was on a particular graph, but we will see in the following how we can work out every time a way to how we can demonstrate it and how we can work out an expression for every kind of graphs. So this is the end point of our calculation, the so-called front door criterion. A set of variables z here again. I'm sorry for my clumsiness, and I will, if you forgive me, I will correct it immediately. And I ask you to forgive me. A set of variables z is said to satisfy the front door criterion relative to an ordered pair of variables x, the cause, and y, the effect, if and only if z intersects all directed paths from x to y, that is, z is inside between x and y in the right direction. There is no unblocked path from x to z, that is, from x to z, there are no paths that are blocked by colliders or by other means, and all backdoor paths from z to y are blocked by x. This is very important, the third point, because and we arrive in this case at the front door formula that is the same that I was showing you before. Of course, all the slides of the lectures are will be I forget until now to give to the administrator, will be given to you from up to now, so will be uploaded, and you can download them from asking from to the administrator, or going, I think, on the website, and I will at the end of the lecture upload all the three so that you can find the formula. I advise you to download the original papers and the original works and the books, of course, but I will give you all the content of the lectures. But let's go back for a little bit to point 3. That is very important. So I ask you, I imagine that I draw a new line pointing from the smoking gene to tar. Okay, so I have this new line, and now I ask you, here in this kind of graph, can I apply the front door criterion, can I do my my calculations? I will, as usual, I will wait for some seconds in order for you to try to even here bet. But in this case, I gave you a precious hint if you to bet with being confident, let's say. I have let's try to watch carefully this graph, and let's try to spot all the backdoor paths. I have a backdoor path from smoking to tar. I have a backdoor path from smoking to cancer, and I have a backdoor path from cancer to tar, or from tar to cancer. So, having a backdoor path from tar to cancer, imagine that this phantomatic smoking gene is something that makes me accumulate more tar in my lungs. Probably I have a protein that binds to the tar that to the substances, to the organic substances that I smoke, and binds and polymerizes it, and so I have a conspicuous amount of tar in my lungs. In this case, I would not satisfy criterion 3. All backdoor paths from Z to Y are blocked by X, because the backdoor paths from Z to Y passing from smoker, working out the expression, the do expression, do tar on cancer, I used the backdoor criterion conditioned on smoking. I was able to do this automagic trick because I was able to condition on smoking. But here I can't block this path, this backdoor path, because I can't measure for smoking gene. I have to pass from my causal variable. And if I can't pass from my causal variable, if I can't block all the backdoor pathways by passing on my causal variable, I cannot apply the front door criterion because I don't satisfy the criterion 3. So, what is the logic behind the front door? The logic is that every time we meet a spurious correlation that can't be measured, we can deal with it if there is a mediation mechanism between X and Y that we can measure. If we know in our causal diagram there is a mediator, a mechanism between X and Y that makes it possible to infer for a mechanism, for a intermediate mechanism between X and Y, such as we are able to define physically what happens. For example, then we can do causal calculation. And sadly enough, we will see in the next lecture that if I haven't got this mediation, and if I have a spurious correlation between the cause and the effect, and I have no mediation between the cause and the effect, then I can never do a causal calculation. We will see it explicitly, and we will work out this explicitly. Now, in this lecture, we gave some heuristic way to arrive to these two workhorses, the front door criterion and the back door criterion, that are there are criterion that makes our life easier when we want to work out, to calculate causal effect, even when we are not able to measure all the variables involved in some cases. In the next hour, we will do two things. We will analyze another criterion. We will analyze the complete set of rules that allow us to do this kind of calculation, that allow us to be always, in principle, able to calculate causal effect. And then I would like to leave open room for questions for some times, because I'm aware that this third lecture has been and will be a little bit dense. So I would like you to try to understand if there is something you're not convinced, if you saw something wrong or unconvincing in my sentences, in my formula, in my exposition. And so please, for every kind of doubt, the second half hour, 20 minutes of the next lecture will be devoted to your questions. So please, if you have any doubt, you can of course discuss between yourselves. Please let me know, and we will see here in 10 minutes at 10:15 in order to go on with the lecture. So thank you for your attention, and see you in 10 minutes. Okay, so hello to everybody. I hope that everybody can hear me properly. And let us begin with our go on with our lecture on causality. And first of all, I would like to ask you for thanks. I would like to ask you for how to go on, because I'm aware that probably the lecture of today has been dense, so probably you would like to go now some working example on the or instead of going on with formal definition and so on and so forth, because I'm perfectly aware that this can kill. So the best thing to do, probably, if there are questions, I'm here to answer. Otherwise, we can go on, and by trying to do some examples of what I some worked examples of what I do intend, and how to use these criterions in order to understand what happens. And of course, each time each time we set up a causal reasoning, each time we want to set up a causal reasoning, we are pretty sure that this is not the situation. I mean, I have a cause X and an effect Y and a single arrow pointing from X to Y. If these are the things, and we are convinced of this model, there is absolutely no need for causal reasoning. Now, let's try to see where the interesting things are. So, one of the possibles is to try to work out some simple example in order to see if we understood properly how things are going on. For example, let's do some concrete example. Let's take this simple example, where G stands for gender, if I am male or female. H stands for hiring, the probability that I will be hired for a given work. And let's ask Q for the qualification. So I can imagine that there is an arrow pointing from gender to qualification. I'm here speaking about the real nasty world, in which, especially in less developed country, there is less room for females to study and to get a high qualification. I'm not stating about how it should be. I'm doing hypotheses on how it actually is. And of course, there is an arrow pointing from qualification to hiring. So this is if you want to understand what's the effect of gender on hiring, the causal effect of gender on hiring, which calculation should you do? Should you use the backdoor criterion in this case, or should you do nothing? Here is my first question. Should you condition, or you should not condition? Well, the silence make me understand that the question I did is incredibly silly. Of course, you should not condition. In this case, of course, the causal effect is simply given by the conditional probability. So the probability of being hired, if I do have a certain gender, is just the conditional probability of having my the probability of being hired conditioned on my gender. There are no backdoor paths. But can you imagine, and here is my question, can you imagine a different model? This is my model, of course. But can you imagine a different model? Is my model taking into account all the possible variables that came into practice when I want to hire someone? And that can be common causes of both gender and hiring. For example, I will pose you a more direct question. Imagine that I want to insert the variable school, the school in which a person studied. How would you connect this school to the other three variables that I draw? To which variables is school connected, and with which direction? This time I won't speak and I won't help. I will wait for someone to speak. If nobody speaks, I will ask directly Andrea Pugnana. I'm sorry, but you're my favorite victim. Okay, someone is okay. School to hiring directly, not through qualification. So for you mean this? I mean, for qualification, I mean you mean reputation of school? No. I mean school. I mean Scuola Normale Superiore, Università degli Studi di Roma o Asilo Infantile Conti Benacci or something like that. Because probably for me, I would probably do rather this. School goes to qualification and to hiring, of course, because the kind of school gets you a qualification, but the reputation of school, of course, gives you a hiring. But let me ask a direct question. Is there an arrow between gender and school? It might be. And in which direction it could be? For example, if my school is, let's say, a religious school that is called Holy Mary School for the Salvation of the Young Lady, in which direction would the arrow point if I have this school in my data set? Here is where the problems came from, because in a line of reasoning, I can say that the school is the probability of having more males than females or more females than males is probably dictated by the kind of school and by the location of the school. My mother used to teach in an ITI, in a technical industrial institute, and his students were 90% male. If one comes in of course, other kinds of studies may have a different distribution, but usually it is highly probable and it is feasible. I'm not saying that is true. I'm not saying that I'm right. I think I'm saying that it's feasible to have this kind of arrow. The school causes the gender, and this, in this case, causes means influences directionally the gender. It doesn't mean that if you are a female and you go to a technical institute, after 5 years, you're a male. You need other kind of institutional, more on the medical side and not on the educational side to get there. But the kind of school can indicate me the gender, because, and some of you could say me, no, it's not like that. The fact that I am a male or a female can dictate the school that I choose. But in this case, my opinion is that the arrow is from school to gender, because why? Before you, let's say, let's try to understand this. Okay, Leonardo say, I don't understand why. It seems to me clearly that it's the gender that determines what school you are likely to go. But for me, it's not important in this scheme in which the effect, the really important variable is hiring, is not important to which school you go. It's important from which school you go out. It's not important that I'm a male, I want to go to the technical institute. It's important the output from the school and not the input in the school. But we could be both right, in the sense that we can draw both graphs, and we can look for a causal explanation in both ways. That, let's say that we can draw an arrow like this, okay? So I ask you, I'm drawing a bidirectional arrow. My question is, can I still do some causal analysis on that? Have I still the hope to do some causal analysis on that? Let's clarify a little bit what I say. Let's say that there is a variable here, an unmeasured variable. I may call it time, that is the time that I consider. If I consider the time of at which I sign up myself to school, then I have one direction. If I consider the time at which I get off school, I have another direction. I have but let's not speak about time. Let's leave it as an unmeasured variable, okay? And let us know nothing about this. can I still do some causal reasoning about this kind of graph? Some hints? Let's try. Let's bet. I would like, for example, Andrea, for you, for Andrea and Leonardo, the ones that are the most active. For you, it's possible to do causal reasoning in this kind of graph? Depends on which variables, I guess. Very good, very good. This is the correct answer. So the variables are the gender and the hiring. So the gender to which you belong and the probability of being or not being hired for the work you are looking for. So this is these are the variables. For example, I can use the backdoor criterion here. Do you see some backdoor path? Given that we observe the school, I would guess that we can, but I am not sure. Well, let's try to apply the rules and let's try to see if, for example, S, the school, do match the backdoor criterion. Okay, first of all, let's see if we block all the spurious paths from between X and Y. And, well, school blocks the spurious paths that goes from gender to school to hiring, because if I go on to the spurious path, if you look here, the only spurious path, it is a child of G, so I guess you can't use the backdoor. But here the question is exactly what you've said. If I take this, if I take this situation, I can't use the backdoor. Can I use the front door? Let's go to the let's go to the front door. No, because you have a direct path to H, so you can't use the front door. And this here we arrive to the truth. So in this case, we have that one of the child of G, S, in this model, one of the child of G can be reached by a bidirected path. I have a bidirected path from G to S. And this is the general rule that we will see in the next lecture. Every time any of the child of G of X of the causal variable, the one in which I'm trying to operate, every time that I can reach a child of X by a bidirected path, that is, by a bidirected link, or by a sequence of bidirected link, I cannot do causal calculations. In this graph, I can't do causal calculation, be careful, from G to H. I can't state the causal. I'm writing, sorry, the causal effects of the gender on hiring. Now I pose another question. Could I do some causal calculation on this graph, on the original graph in which it is really marvelous that I'm so clumsy using this wonderful object, but you are data scientist. I think you have wonderful feats of imagination. So please imagine a wonderful arrow pointing from school to gender in the sense that I proposed earlier. That is, the important thing is when you go out and when you do not go in. So the school determines in output the distribution of the gender, and what I'm looking for in this kind of calculation, what is important to me is the output. What would you do? For example, again, Leonardo and Andrea, what would be the first thing that you would do having this graph with an arrow pointing from S to G? I can give you three different options. Control for S with the backdoor criterion, you mean? Andrea suggests to control for S with the backdoor criterion. And this is correct, but I would do something before. Can someone guess what I could do before? What I should do before? Even before of controlling for S? Well, let's arrive to it. Leonardo, are you convinced by my argumentation that the arrow point from S to G, or you would still we would still say no, I don't agree. For me, the path is bidirected or even directed in the other situation. And if you're still convinced of your argumentation, how could you prove me wrong? How could you say, no, Malvaldi, you're wrong, and I can prove it? Sorry? Oh. Sorry, but I made a mess. Okay. Okay, sorry. I guess it depends on what exactly we mean by the various variables. Yes, but I mean exactly, and here I'm going to the I'm going to what I am and I'm going to say precisely. The variables that I mean are exactly the one that I said. Gender can take the value male or female. Hiring can take the variables yes or no. School is exactly the kind and the name of the school that you went. So both the kind, a technical institute, a classical institute, at a scientific lyceum, and so on and so forth, and it's a specific name. A specific name would go because if I say Liceo Classico Giosuè Carducci, I know for sure that it's a classical school. And the qualification is the degree that you get. If you get the first degree, if you get you get a diploma, if you get first order bachelor, and so on and so on and so forth. But the first thing that you should do is related to point 3. Test if the graph is coherent with the data or has to be rejected. Remember that if I am able to draw a causal graph, and I'm able to calculate conditional probabilities, if my graph is correct, it has to respect the recursive decomposition formula. So I want to see that the joint probabilities are equal up to the experimental error that I can estimate to the product of the conditional probability. So if you remember, the first thing that I should do before trying to extract causal information for my from my graph is actually trying to see if my graph is feasible. Because if I find that this recursive decomposition does not work, if I find strong dependencies between my variables that are not predicted by the data set of parents that I set up, this means I'm wrong. So remember that in this game we can always play with our brain and draw a directed graph and connecting the variables that we wish to consider. We can, but we can control, we can test if the graph is coherent with the data or if it has to be rejected. So being a statistician, we should never forget this. And this is a crucial point for me because, as you saw, there is often disagreement and perfectly allowed disagreement, because we are scientists. We are inferring things, not just merely observing things. But there is often disagreement between which variables are there, how to define variables, which direction should the arrow go. And then you have to test. You have to test whether the things that you are saying are correct or not, given the data that you are given. So I think that this is the best point to conclude the lecture and to see if there are questions, because as in every kind of statistical analysis, let it call it causal analysis or other kind of variables, what we should every time do is look if the instruments we are using are the right instruments to tackle the problem out. And after that, we can go on by playing with our instruments, and let's look if these instruments are do give us the correct answer. If, as you saw, even in a apparently simple problem like the gender hiring problem, that is, I may guess, one of the problems in which you as a data scientist will be involved here and now in your career, it's not so easy to deal with the proposal of a new variable and how to integrate this new variable into a working scheme. So, first of all, when you insert a new variable, always test for that variable. So, I think the best thing up to now is to ask you if there are some question about what we saw in these lectures, and if there is there are some doubts and some incoherencies, something that you would like to discuss. I will now, if there is no question, I will ask directly Luca Pappalardo if because I know that he's a very clever and up-to-date person. So if he has no question, I'm quite sure that every one of you is up to the point. So Luca, are you there?
Hi, Marco. Yes, here I am. No, maybe just to socialize a curiosity that I already told you some days ago. So it seems to me that actually the reasoning about the causality is pretty complex and maybe made more and more complex as needed, right? For example, as in the case for gender and for reputation of school and so on, one may complicate, let's say, the reasoning as needed. No, an interesting thing, since you like to make examples about soccer, about football, let me socialize an idea that is one interesting thing to probably make an exercise on would be to understand what is the impact of the COVID-19 pandemic on a prominent behavior of football teams, that is the home advantage. We all know that when you play at your home stadium, you generally play better or worse. It depends on the situation of the team, right? So, but there is a home advantage effect. Maybe it would be interesting to investigate, to make an exercise maybe for next lessons on how the COVID-19 may influence this home advantage effect in football, but for all the other sports. And here I imagine that are probably 2 or 3 variables. The first one is people at the stadium or not. So a variable that you account for the possibility of people to stay in stadium. And then there is the probably home advantage variable. And then there is another variable that may be how strong is the opponent, something like that.
Well,
and so it would be interesting to make a reasoning on that. That's, you know, my curiosity, my question that I want to socialize.
yes, this is thanks, because I was willing to give an exercise to draw a scheme. I was wondering, and I was thinking about football, but so I was proposing a different pathway, but I will accept your suggestion. So for all the people that would like to share this kind of ideas and would like to test themselves, and we will start next lecture from here. We will you can choose between two exercises, and I will write it down and send to the administrator, so that we have written down all the things, but you can choose between one of the two situations. The first one is the one proposed by Luca, cioè that is a causal model for the home advantage given, so necessary but not limited to, these three variables: the people at stadium, present or not present; the home advantage, that is the variable x that we are calling the cause variable; and the result. The result, of course, the result in terms of the opponent that you face, because if you can have even if there is a home advantage, if you are Benevento and your opponent is Juventus, no, I did the wrong example, you can win already. But if you are a low classified team and your opponent is a high classified team, no matter the home advantage, you will probably lose. But this is the first example, and I will write it down in all the variables in order to see. The second example that I would like you to think about it is the effect of the coach on the performance of a football team. How to model a causal model, to model the effect of a coach on a football team. And here the variables are, of course, the team, of course, the coach, and of course the result. You will, I think, discover that it's not so, it's easy to find many models. It's not easy to be convinced of just one model, and it's sometimes you draw up a wonderful model and you ask for data and you discover that you haven't. So thanks, Luca, for this suggestion that is very useful. And to finish with this, remember that causality is really almost a newborn science. And this means that probably something that came in your mind and that you can look as an exercise to understand things can easily turn on into an active research team. So there is, if you have a causal model and you have plenty of data that have been produced without still a causal model that is under the model, then there's probably room for a serious scientific causal analysis. So I thank you all for your attention, and we will see you on Friday. We will begin by analyzing causal models that you propose, and we will go on by algorithms, by discovering how to set up an algorithm that will always say me if I can do causal calculation or not, with no need to crashing our head into graph by our intuition and by our forecasting abilities. I encourage you to exercise on this because it's useful to understand graphs, but as a present, it's not actually necessary. So thank you all for your attention, and we will see you on the next lecture on Friday. Let me know if you prefer another day of the time, if you prefer 10, 12, for example, and we can arrange and manage for it. Thank you all very much for your participation.
Grazie Marco.